Yeah, I have fewer lectures than Bert, so I'm not as well trained in this. Yeah, okay, but now we're recording. Yeah, so back to the notebook. Yeah, so like I said, we can. So the goal of a probabilistic programming language is also to allow a user to basically specify a probabilistic model as easily as possible. So if someone has already done this math a bit, where you have some priors, I have some likelihood, I've chosen distributions for these, or I've chosen parametric probability distributions for these p's, these densities, then I can fairly straightly from these equations encode this into a computational graph here. And so this is also why we needed to install this GraphViz package for the course, because some probabilistic programming languages, so not all, but Formulab is definitely one of them, that allow you to visualize the underlying computational graph. And Formulab generates something that matches the our hand-drawn factor graph fairly well. Of course, once the factor graph gets really complicated, when we get a lot of terms, we get a lot of likelihood components, or a very hierarchical model, you'll see this in the dynamical systems lecture. Then the generated computational graph looks a bit different from this one, because this one has a bit more detail that is purely there for the underlying engine. Yeah, but still, so this prior node f of a has two parameters that are clamped. It will send out a message upward to this unknown variable theta, and this likelihood node will absorb this information from x1, and x1 is given a value here in this placeholder node. And then this thing will send out a message downward. These two messages will collide, and we'll be able to compute a posterior. So message 1 and message 2. You can see that here. There are dotted lines showing that this node is drawing information from these two edges, and this node is drawing information from this edge. Yeah, so absolutely feel free to interrupt me with questions. I'm just... Yeah, okay, so Stefan has a question. How does Formulab know how to draw the factor graph? Yeah, that's a good question. So we are defining a factor graph here, and so then we're adding variables to that. So first we're adding a random variable theta, and then we're going to add a random variable x1. But once we define x1, we'll say that this thing depends on theta. So whenever we do at rv, our Formulab creates a node in the graph. Whenever we say that one of these variables here, or this node depends on another variable, we'll draw an edge between them. So basically, up to this point, Formulab only knows this prior node and this likelihood node, and it has an edge between them. So here, technically, it also says A is and B is, and so A is. So because we've set that, Formulab also generates this clamp parameter and this clamp parameter, and it knows that this node has 3 edges because it's defined to be of a beta type, and a beta distribution always has 1 outgoing random variable and 2 parameters, A and B, which had now been clamped by us. And so here we'll say that x1 has is a placeholder, as in we're going to feed data in there later. And so it'll generate this this node, and it will say that this node is of a placeholder type. So now internally, Formulab has this this graph structure with all of these nodes that are both defined and inferred from the probabilistic model, including all of the edges. And so GraphViz is just a way to GraphViz will just start with some initial node, and then we'll sort of use a particular drawing scheme to start adding node to this graph and then drawing edges between that. And you basically don't have any control over how GraphViz puts nodes together. And that's also what you see here. So in all of the lectures, or what's conventional in all of the literature as well, is that the observed variables are down here and the priors are up there. And usually you read these factor graphs, especially if they're defined over time, you read them as, so left is the past and right is the future. So there's a left to right direction in these factor graphs, and there's also top-down influence. The prior is some sort of top-down influence, and then the observations is some bottom-up influence. So there's a directionality for how you would define the factor graphs if you're writing them or you're drawing them manually. And just GraphViz doesn't know about this at all. So it'll generate, so this thing is upside down, as you probably already surmised. And once we define larger graphs, you'll see it becomes a bit of a mess, because GraphViz will just start with one node, add another node, add another node, add another node. It'll try to do things, it'll try to place things in parallel, but you can see here already that it's failing to I mean, these two things are not exactly the same. But so GraphViz basically just takes all of the information that Fornilab has, this graph specification, and then starts drawing a bit according to its own scheme. Does that answer your question, Stefan? All right. Yeah, I'll continue a bit with the notebook. Again, I'm just repeating what's already in the YouTube lectures. I'll try and see if I can find some points that remind me of sort of additional exposition. It might also be fun to look at alternative probabilistic programming languages. So here we're using Fornilab. That's something that's developed by our own lab. We are one of the sort of few academic labs that have started with the probabilistic programming language, and we're also well known in the community. And so if you're familiar with neural networks, for instance, it used to be the case that, so when I started my PhD nearly 10 years ago, you would, if you wanted to write, or if you wanted to do computations with a neural network, you would have to manually write down a function and manually apply the chain rule to get your derivatives and then or your gradients, and then specifically code out all of the gradient functional forms when you're doing backpropagation in this neural network. There were some tools available, but they were mostly just for very specific architectures in neural networks. But 2013, when neural networks started making a lot of noise, when they first caused this major increase in performance for ImageNet, an object classification problem in computer vision, there were a few academic labs that started making these larger toolboxes that would automatically allow you to do backpropagation in these computational graphs. One was called Cafe, you had Theano. They were all by the big neural network labs. And then over time, these notebooks were very successful, but they were, their development was a bit too slow for some of the industrial giants, Facebook and Google and stuff like that. And so these companies started developing, they started investing in developing a toolbox of their own with which to specify really large neural networks and have all of these annoying, tedious operations done automatically. And they realized that if they would open this up, if you create open source code for this, then a lot of people would adopt their code and people would basically write neural network architectures that Google could use directly themselves. It's also like Colab. Everything you write on colab.google is automatically transferred to Google, so Google has ownership of all of the neural network designs that are built using Colab. And so basically the same pattern of development is repeating itself now for probabilistic machine learning. There are, so in the past you would have a lot of, people do a lot of stuff by hand. You would infer all of these posteriors, derive the update equations by hand, and that's what you see in the papers. There have been a few automatic statistical inference toolboxes. For instance, Stan is a toolbox for statistical modeling and high-performance statistical computation. It uses another form, so we're using variational inference. We'll get to that later in the course, but it mainly uses something called Monte Carlo sampling. This has been around for a while, but this is also not the most straightforward package to use. And so a few academic labs are building probabilistic programming toolboxes now to automate a lot of the inference tasks that you required in order to do probabilistic machine learning. So one of them is Pyro, and this is something for Python, for instance. It has a different engine that Formulab uses. Yeah, feel free to have a look. It's has a bit of a steep learning curve because it combines a lot of things together. It's under the hood, it uses PyTorch, so some of the function approximations are based by neural networks in there, but it also means that you need to know a little bit about neural networks before you can really get started with Pyro. There's also something called Turing.jl, which is another Julia software package that uses Monte Carlo sampling instead of message passing to automatically infer posteriors. But it has relatively the same structure for specifying a probabilistic model. There's some Julia macro that says, like, I'm now defining a model. I give this model a name, and then I can say that there's some variable that is unknown but distributed according to some distribution with fixed parameters that I encode. These are prior parameters that I fixed. And then this sigma becomes one of the parameters for this thing. So that's a likelihood. Yeah, so a lot of these academic toolboxes. There's also one called Infer Net. That's another message passing toolbox. That's for .NET and C#, so Microsoft. Stan has been around for a while. Turing. So Julia has actually a lot of packages. There's also something called GenJL and SOSJL. They're all different ways to do to automate inferring these posterior distributions, which is called probabilistic programming. So again, there's this macro says I'm defining a model now. Now I'm calling it M, and then I have these distributions. So I'm indicating that these unknown variables are, and I'm not assigning a value to it, but I'm indicating that I have some uncertainty over this expressed by a probability distribution. And so you would like to do some form of inference, pred alpha, and then it under the hood does in this case also a Monte Carlo sampling step. So people are also still sort of testing ways to automatically do probabilistic inference, probabilistic machine learning. But in general, all of these packages for various programming languages, we're sort of converging on a convention for how to specify a probabilistic model. It's going to be something that matches this setup with some name for a model, and then indicating that some variables are observed and some variables unobserved. Yeah, so as you can see, there's a lot of similarities already with how you would define things. The specifics are going to converge over time, and what we'll probably see in a couple of years is that that big companies will adopt these toolboxes, and it will get expanded, and it will be much easier to use probabilistic programming. So you're one of the sort of early generations that are probably going to benefit the most from this new advance, this new breakthrough in probabilistic machine learning. So Google is already trying stuff out. They have something called Tensorflow Probability. It's more TensorFlow than probabilistic programming at this point, but they are sort of interested and they are sort of eyeing some certain software packages. I wouldn't be surprised if at some point they buy up ownership of some of the packages and then start working from there. A bit like how TensorFlow got started in the first place. Yeah, so that's some exposition as to so what is probabilistic programming? Do we need formula to be able to do probabilistic programming? No, you can use a bunch of other packages. So within Julia, I've just shown you 3, Turing, SOS, Gen. And then outside of Julia, you'll have Pyro for Python. It's a well-known one. There's Infer Net for C# and .NET. And yeah, so Stan has a C++. And in general, there's quite a few languages for different underlying programming languages. So something called Birch, which is new as well, Probabilistic C. Yeah, so Turing, Gen are on there. Edward and TensorFlow Probability and Edward 2 are very similar. Pyro I've just shown you, Stan I've shown you, Birch is for C++. Yeah, Church is a really famous one of the first ones. Yeah, if you're interested in programming languages and development of probabilistic programming languages, then there's a really rich history of people, 50 years ago already saying we should develop a way to easily specify probabilistic models and automatically infer stuff in them. So are there questions at this point?
Yeah, I just had one question.
Oh, yeah. Go ahead, yeah.
Yes, so if you can go to the message passing part of the code. Yes, I guess.
This part?
Yeah,
yeah,
from this part. So from the part where it actually shows the messages in the diagram.
This part, yeah.
Yes, so I just had a question here, which was, so we defined the factor graph in the previous code, which says, factor graph 1 equal to like a factor graph, and then we draw the factor graph. And then in this part of the code, where do we actually specify which factor graph we need the message passing to be done on?
Yeah, so whenever you call this sort of message passing algorithm, so it's a bit like in Windows, if you have a window open, or so if in MATLAB, if you are going to, you might have a few windows open, and you might have named all of these windows like figure 1, figure 2. But if you just give a generic code, like alter my figure, like change my axis, rescale them, make the background white or something, or black, whatever, then it operates on the last used window, the window that you've defined last. So then that's the one that's in focus. You can click on a window and that changes focus. So that's basically what's happening here as well. I've defined factor graph. This is sort of the most recent definition of a factor graph in memory. So whenever I do message passing algorithm, it is going to default to the most recent factor graph defined, which is factor graph 1. And so here I've, oh no, hold on. Right, okay, this is still the message stuff here. Yeah, so here I have factor graph 2. So now I have to find a new factor graph. So when I do anything here, I'm operating automatically on factor graph 2. Now I specifically need factor graph 2 because this draw command, GraphViz wants to know exactly which factor graph it needs to draw. And that's where I need it the most. I believe I can, within this message passing algorithm, provide a keyword argument saying that give me the message passing algorithm for this specific factor graph, but it's just going to use by default, it's going to use the most recently defined one.
Okay, so if I'm writing like a bigger code where I've defined a lot of factor graphs and I need to call some previously defined factor graph, I can just give it like an argument in the message passing algorithm function.
Yeah, I can look it up for you, but that's indeed what you can do. Yeah. Yeah, this will probably take a while. If I'm not entirely sure where.
Yeah, that's fine. Yeah,
we define this. So I'm just going to quickly go to the other question and then.
Cool. Thank you.
Yep. Sveta?
Yeah. Hi. So I had a question regarding the graphs for multiple questions for the job interview. So we had a simplex graph, if I'm not wrong.
This one? This is the multiple questions.
Yes. Could you go down? Please scroll down.
Further down?
No, this is clear. The graphs with the PDF distribution for each of the message. So I just wanted to.
Here, this one.
No, after this, the graphs. Yeah.
Yeah. Oh yeah.
These are fine. The next set of graphs.
The score questions.
Oh, sorry. Oh yeah, sorry. Score question. Sorry, my bad. Yeah.
Okay. Yeah.
Could you go further down?
Yeah.
I think it's this one. Can you go further down?
You want the messages visualized?
Yes, this one. Yes, yeah, this one. Yeah. So after this, there were graphs for the marginal of theta, then for the prior. So could you explain this a bit more, or how the parameters for alpha, how they affect? And I could not understand what was the x and y axis of the graph as well.
Right. Yeah. So that's a bit difficult to visualize. I think you really need this picture to understand the following pictures. So a simplex is it's a structure in a lower dimensional space. So what that means is here I have a three-dimensional space. You can see this three-dimensional coordinate system, and then I've defined this triangle here, and it's a plane. It's a plane that cuts this three-dimensional coordinate system in a very specific way, namely that every point on this triangle, every point on this triangle, if you sum the values of the elements in that vector, you'll get the value 1. And so that's actually what we need. That is what a Dirichlet distribution is. The Dirichlet distribution is a probability distribution over vectors that sum to 1. And that means that for a three-dimensional coordinate system, a three-dimensional space, a Dirichlet distribution is a distribution over this triangle, which is a two-dimensional object. And it basically describes it. So this probability distribution, if it's uniform, that means that every possible point on this triangle is equally probable. And if it's not uniform, if it concentrates in some area, then it means that some location on this triangle, some location on this lower dimensional space has higher probabilities than some other location. So so I cannot. It's kind of hard to visualize the Dirichlet distribution on this three-dimensional, like this two-dimensional plane cutting a three-dimensional system. I took this picture from the Wikipedia page for simplex, or for the Dirichlet distribution, I think. Yeah, so no. Yeah, I don't know exactly. Oh, here it is. Yeah. Okay, so I stole this particular picture from the Wikipedia page that describes a simplex. And so the reason I say why it's a lower dimensional object in higher dimensional space, because this is just a 2 simplex in R3, but you can imagine that as we get more options in this question. So now these are categorical distributions with 3 possible answers. Let me just try and find. Yeah, okay. So x1 has 3 possible options, 0, 1, 2. But I mean, I can define this as long as I want. I can give as many options as I want. That's the whole point of a categorical distribution, that I don't have a binary option between right or wrong, but I might have n possible answers, as long as it is discrete. But if this thing goes from like 0 to 100 or something, that means that I have a 100-dimensional random variable here, 100-dimensional categorical. That means that the Dirichlet prior that I put on that is also a 99-dimensional simplex structure in R100. And those things exist. So you can see that here. This is a line in a plane. So that's a 1 simplex in R2. Then I have a 2 simplex in R3, a 3 simplex in R4, etc. You can keep going. You get these really complicated structures. And for us, this notion of a simplex is maybe not the most important thing. The most important thing is just that we define the probability distribution over numbers that sum to 1. So even if this x1 is 100, I get 100 options, then my Dirichlet parameter vector will also just be 100 numbers, but they should all sum to 1. Or the data will be 100 numbers, but they should all sum to 1. But if we're going to visualize a Dirichlet distribution, and in this case, the easiest one to visualize is this this triangle in 3D space. But we can take this triangle and basically squash it flat on a 2D plane, because it is a 2D structure. It is a plane in 3D space. It is just a 2D structure. But if I squash it flat, then I don't have a unit square. I just have that triangle. So, but if I have this flat structure, then I can suddenly visualize probability density functions again. I can use contour or some other function to specify that some particular area on this triangle has higher probability than some other area. And so you see that here for these parameters, alpha is 1.5, 1.5, 1.5, then I get something where almost all of the mass is located in the center, but also spreads out quite nicely. Then as these alpha values increase, you can see it's really concentrating in the middle. So with high probability, this parameter vector is something like 0.5, 0.5, 0.5. So it's a bit harder to read off the axes indeed, but you should just think of this as there's some orthogonal line. So the center here that's this orthogonal line, or the line orthogonal to this basis, and another line orthogonal to this basis, another line orthogonal to this basis, and then where those 3 lines intersect, that's that point. So this point has 0.5, 0.5, 0.5. Yeah, so that has high probability, and then for instance this point here, 0, 1, 0, that has low probability. So these 2 upper cases are for when these alpha parameters are all exactly the same. But you can yeah, this distribution is really quite flexible. You can define this with quite unusual parameters. Then you get sort of a weirdly shaped blob that resides somewhere in this triangle.
So if I understood you correctly, do the sides of the triangle represent each element of the of alpha vector? No, or is it the theta, each element of theta?
Yes, yeah. So yeah, that might be a bit confusing because here it says x1, x2, x3, and then in this example I have x1 and x2 for the outcomes of the categorical variables. But it's theta. We have a Dirichlet distribution over theta. So theta is also a three-dimensional vector. Theta needs a sum to 1. And in this particular example, theta 1 corresponds to the first element of theta, theta 2 corresponds to the second element of theta, and theta 3 corresponds to the third element of theta.
Okay, so
So I probably misread this one as well, because it needs to be a number that sums to 1.
Yeah. Okay. So could you go back?
You can see maybe that. So if in this particular corner, I have value 0 for let's see. I have value 0 for x1. I have value 0 for x2, and I have value 1 for x3. So 0, 0, 1, that sums to 1. In this corner, I have, I have 1 for x1. No, sorry, I have 0 for x1, 1 for x2, and 0 for x3, so that also sums to 1. Every point here is, if you sum all of the values of x1, x2, x3, which corresponds to theta 1, theta 2, theta 3, you sum of them, they will all sum to 1. But the parameters of the distribution, those alphas, those concentration parameters, they don't need to sum to 1. They can be larger than that.
Okay.
Sorry, I interrupted you.
No, that's okay. So the darker the region is, it means the higher the probability. It is that theta follows that set of values given alpha, right?
Yeah. So here I've defined 3 alphas or A's, and they define the probability, the height of the probability density. So the probability density here is quite large. It's quite concentrated here, and it drops off in this direction. I realized that this is just really hard to read out because, so I was unable to replicate these figures with like 2 axes here. I only have this particular axis here. And also there's no color bar here for the probabilities that correspond to these colors. That has a lot to do with importing matplotlib into Julia, because some of you can already see it here, this levels quark is not used. I defined n levels is 200, that's not picked up by Julia. This color bar is also not correctly shown.
Okay.
But so these figures are just to give you an impression that we've, so this theta is a very specific object. It's not, so far we've only worked with random variables that are either defined discretely, as in they're 0, 1 or 0, 1, 2, or they're real valued, as in the Gaussian distribution. They go from -infinity to infinity, and you can span that into as many dimensions as you want. But this theta is a very weird particular random variable in that it is a vector, but the elements of the vector must sum to 1. And that gives you sort of this weird geometric interpretation of what the values of this, what the values that theta might take, which is this triangle in 3D space. And in the end, we're working with probability distribution, so it's not just about visualizing what values theta might take, which is just this triangle, but it's also about visualizing with which probability theta takes certain values. And we do that here by, you can see that here as well, we do that here by in some sort of color plot that so areas of dense color also give you high probability. And I've tried to replicate that here in this situation. And it's mostly just to, these figures should just mostly be read as, if I change these parameters, then this blob starts moving around. And I do highly encourage you to take this notebook, plug in different values for either for the outcomes or for the priors, and you'll see this blob move around a bit. That gives you some intuition for what that means.
So if I'm understanding correctly, then if the second element of alpha is the highest, then the corresponding probability, that is the element of theta, will be higher. So it will move down along that side, right? And
Yeah.
if we have two elements of alpha to be roughly the same, then it'll be bigger. The contour would, the area of the contour would be bigger because it will try to move on both sides as well.
Yes, exactly. Yeah.
Okay.
Yeah.
Okay.
Well, hold on. No, that's inversely true. So here you get alpha 1.5, 1.5, 1.5. So, I mean, they're all the same. So the most density will be in the middle. But you can see it's fairly spread out. And now I increase the concentration for each element, and you'll see that this probability density function. If you remember a Gaussian, if I decrease the variance, then this thing will start to spike, something that we call it's concentrating around some value. This is also what's happening here in the Dirichlet distribution. So it's true that each concentration parameter is sort of important for each element of the theta vector, but they're called concentration parameters because the more they increase, the more this distribution concentrates on a particular value.
Okay, right. And just to clarify once more, it's only for theta that the sum of the elements of theta add to 1. Is it not the case for other conditional probability distribution?
Well, there are some more exotic distributions where you also need that property, but you won't see them in this course. It's mostly here because if you remember the categorical distribution, so the categorical distribution is basically sort of a multivariate extension of the Bernoulli. So there'll be, with some probability, it will be option 1, and 1 minus that probability will not be option 1. Then we'll have another option. With that probability will be option 2, and 1 minus that probability will be option 2, not option 2. And then we'll have option 3. So we'll have with some probability will be option 3, and 1 minus that probability will not be option 3. In the binary case, this is you'll have a particular simplification, namely that option 2 is actually exactly the same as not option 1. Whereas in the multivariate case, the generalization, option 2 is not the same as not option 1 because there's also a third option that you could go to. So whereas in the Bernoulli case, you need your one parameter suffices to describe either yes or no of that particular option. In the categorical case, you need one probability essentially for every option, and then you can also, I mean, there's still this constraint of 1 minus that probability is not that particular option, but that doesn't necessarily correspond to any of the other options. So you do actually need one parameter for the probability of each option. But in the functional form of the categorical distribution, which is also you can see it has the same functional form as the Bernoulli. There'll be the option raised, there'll be the probability raised to the power of the option. And in order for this thing to be a valid probability distribution, all of those individual probabilities of the options have to sum to 1. And that means that if you want a prior for that, specifically also a conjugate prior for that, then we need a distribution over vectors that sum to 1.
So the mu case need not add to 1, but the prior definitely has to add to 1.
Yeah. So hold on. Yeah. So the categorical distribution, it's another way of looking at this is that the categorical distribution is a one-hot coding scheme. So out of n options or k options, I will pick 1. And so the probability of picking that particular option also has to, maybe that's not a good explanation, I think. Forget about that. Yeah, but so the categorical distribution, we're just going to pick one of the options, and that option might correspond. I mean, you can define a categorical distribution not just over outcomes 0, 1, and 2, but you could also do apple, pear, banana, or something. It's more that there is some probability assigned to each of the options, and the options they can be anything. They don't have to sum to 1. But the probability of picking each of the options has to, the total probability of the options have to pick to sum to 1.
Yeah, okay. So I just realized have another doubt in the distribution. Could you go to the tab, the tab with the theory part for this?
Yeah.
Yeah. So XK denotes that whether that phase was rolled, right?
So this is a die. Yeah, exactly. That face is rolled. Yeah.
So why do we not have like 1 minus mu k for the rest of the options of the die?
Well, it's related to what we just discussed in that in the binary case, if I have a coin, and if I know that it's not heads, then I automatically know it's tails. So that means that I can encode those two options with it's either heads or tails. I can encode that with there's some probability for heads and there's some probability for tails. But when I know that tails is 1 minus heads, if I encode these two options at 0, 1, that means that I can describe the probability density fully with just to the power x and to the power 1 minus x. And I can actually use the same parameter for that because in the case of Bernoulli, they also have to sum to 1. It's either if I have that one parameter theta, and say that's 0.7 that I'll get heads, then automatically I will have 0.3 probability that it will sum to tails. So that's why in the Bernoulli functional form there's 1 minus theta, because that automatically encodes the second option, the second possible outcome. Whereas here I explicitly describe each of the outcomes as, so you can think of a Bernoulli as a special case. So k is 1 to capital K is 2. I'll have mu1 to x1 and I'll have mu2 to x2. But in the Bernoulli case, because it's binary, we know that mu2 is actually 1 minus mu1. So that's basically what's described here. You'll have mu1 mu1 to the power x1 times 1 minus mu1 to the power x2. And we know that x2 is 1 minus x1, so you can basically replace that. So overall, we'll just get mu1 to the power x1 times 1 minus mu1 to the power 1 minus x1. That's the specific Bernoulli case. And because we don't know this anymore in the categorical distribution, if we know that it's not option 1, then we still don't know whether it's option 2 or option 3. That's why we have a very specific, a very explicit description of there's a probability for each possible option.
Yeah.
Does that help relate categorical to the Bernoulli?
Yeah. I think I got a bit confused, but yeah, now it's clear. Yeah. Thanks.
Okay. Yeah. So Stefan has a question. If the sum is always 1, why is it then a plane and not a quarter of a globe or an eighth of a globe? So the so what you're thinking of is the unit circle. And the unit circle is defined in the Euclidean norm. So that means you're squaring and everything. But here we're not squaring, we're just summing. Does that help? So there's this famous picture. I'm not sure if this helps. Maybe your yeah, it's this picture, but it's a bit. Yeah, here it is. Yeah. So if P is, so in an LP norm, you would take a vector, you would raise the elements to some power, sum them, and then take the square root, for instance, to get the magnitude or the length of that vector. And so that power that you raise it to, if you use P is 2, it's called the Euclidean distance of that vector, the Euclidean norm of that vector, then you'll get something that looks like a circle. So this particular point is the same length from the origin as this particular point, according to an LP norm where P is 2. You're squaring all of the elements, summing them, and then taking the square root again. But if you choose a different value for P, so in this case P is 1, then this particular point is the same distance from the origin as this particular point. Now we're not squaring the numbers, we're just summing them. So we're also not taking the square root anymore to sort of invert that P operation, but we're just summing all of the values, and that gives you, that gives you a line, straight line. All of these points are the same distance to the origin according to an LP norm of P is 1. Now, I mean, so the wonderful thing about LP norms is that if you change that P, you'll get all sorts of weird behavior out of all sorts of weird norms and stuff. But basically, this is the picture to keep in mind. Does that help? Oh yeah, yes, thank you. One other question. Why do we denote distribution as X tilde distribution, not as X is distribution? Furthermore, why do we then say that a sum of two distributions, X and Y, follows from Z is X plus Y and not Z follows X plus Y? It's still a distribution, right? Well, I mean, that's a good question. I think it's mostly a convention thing. So this tilde operation is used in a variety of ways. So we can also write, for instance, this. So X sub I tilde Gaussian 0.1, and that means that we have a specific observation of a random variable, and so we do have that value of xi. So we might say that xi is 1. But we also have the additional information that x is distributed according to a Gaussian with mean 0 and variance 1. And this is just one particular sample of that. Say that I were to repeat the sampling process. So you can think of this, I have some sensor and I make a recording. I measure something with my sensor. I'm going to write that down and then I measure it again. And the same time, or the second time, it might not be different. I might get an entirely different measurement. And that's sort of the crux of random variables. It's if I had a very deterministic world, then I would take the sensor and I would measure the same thing and I would always get exactly the same value. And then I could just say, well, this variable that I'm measuring, this thing that I'm measuring just is that particular value. And originally this tilde notation just means that, okay, so I have made a measurement, but I know that this measurement is from a Gaussian distribution. So next time I might get a different measurement, but that I know that overall, if I were to, in a frequentist perspective, if I were to measure an infinite number of times, then I would get that all of those measurements would be distributed as a Gaussian distribution. That's roughly where the tilde notation comes from. So the Bayesian interpretation, we adopt this convention in that we have some subjective belief about this random variable. So we believe that it's distributed according to some distribution, and someone else might have a different belief about that. So it will be incorrect to say that this particular value is distributed according to some distribution, because it just means that I believe that this X is distributed according to some distribution, and I do not know that for sure. So I would like to avoid the use of this equals operator. So in mathematics, equals is a very rigorous thing, right? You have to, if you want to prove that something is equal, you have to sort of show that both directions of the equation sign are implied through some reasoning steps. So your follow-up question: if I say that Z is X plus Y, so in that case you might say I am constructing Z. this new random variable z, I am constructing that from two other random variables. And this construction process is known, is fixed, is deterministic, because I'm doing this, and I don't have any uncertainty over whether z is actually x plus y. I know for certain that z equals x plus y because I have constructed z to be that. And then we can compute what z is distributed according to, purely from that x and y are distributed according to something, and then we have these rules for adding random variables. So we could then once again say z is distributed according to some distribution. That is the result of z is x plus y, where x and y have some distribution. Does this answer your question, or are you still confused about something? It's morely, it's a notation thing. It's a semantics thing. It's not entirely a convention. It also reflects back on sort of the interpretations of probability. Okay, yeah, that's good to see. Yeah, are there any more questions? I'll fill up 5 more minutes with exposition, and if there are no questions, then I'll stop the lecture. Yeah, so this is in this probabilistic programming notebook. I'm introducing you to message passing. Well, I mean, Bert has also done that, of course, in the theory lectures. But why? So there are tons of probabilistic programming languages. Why are we working with message passing as a way to automatically infer posteriors? I think message passing is first of all, a very efficient way to do these computations because you can distribute them according to, or you can have all of these computations done locally in a computational graph. That means that if you're designing an algorithm for a specific computational hardware, then you have some freedom to place certain computations on various components of a hardware. I think message passing is something that really shines when you are, in the back of your mind, you're thinking about what is the computational architecture that I'm going to perform all these computations on. So our group Bias Lab is part of signal processing. So if you would like to use all of this stuff, this probabilistic machine learning, Bayesian machine learning for signal processing, you can imagine that we can design this factor graph on a desktop computer, and we'll put it on some smaller device, and it will have to it will have limited computational resources. So it must also, you might think of 2 small devices, and then you can distribute computational load across these smaller devices. There are in other probabilistic programming languages, for instance, Pyro, where the underlying engine is a neural network thing. That's more, so suppose that I have like a big computer, a big compute server, lots of GPUs and TPUs, then I'm just gonna have this neural network engine do all of these computations in one place, and yeah, and then just try to estimate all of those posteriors at the same time. Message passing is also very useful for dynamic systems because there you have this factorization over time. So I'll do some computations at this particular time point that gives me a posterior, for instance, state estimate when I'm trying to filter a signal. And then time moves forward, and I can recursively apply the same structure. So again, I do all of these message computations, then move forward. And something like a neural network system will have to sort of wait for a very long time until it's observed quite a few samples, and then store all of those samples in some buffer, and then do massive amounts of computations, and then it'll be trained, and then you can move forward again. And message passing is a very efficient way of doing all of these computations, automating probabilistic inference. I think it's very suited for you guys as a target set of students. But I mean, there are other options. Later in the course, we'll move into variational Bayes, which is sort of a really fast analytical approximation technique. When you don't have these conjugate primes, don't worry about it. We'll dive into it later. There are also other techniques such as this Monte Carlo sampling that I showed a bit earlier. That also requires sort of a larger computational engine, some larger compute server to be able to do things. If there aren't any more questions, then I'm gonna quit the lecture. So to give you some perspective, the Probabilistic Programming 3 lecture is in the new year, I think. So in case, oh no. Yeah, so 22nd of December is the third Probabilistic Programming session. Yeah, okay, so I'll see you still before the end of the year. Before the new year. Yeah, so there will be a Probabilistic Programming assignment for the course, as discussed on Piazza, and I posted an announcement as well that in the first Probabilistic Programming lecture, I said that we would probably release that somewhere at the end of December. You will have Christmas break to work on it. That's no longer the case. That's no longer the plan. The TUE has mandated that there won't be any assignments over the course of the Christmas break to give everyone the opportunity to not focus on your studies during the Christmas break. So we'll hand that assignment out once you return to campus, to class, and we'll try and give you enough opportunity to do the assignment before you have to start focusing on learning for the exam, studying for the exam. All right. Yeah, I will stop recording now.